So hello and welcome to this manufacturing process technology part 2 module 46. We were talking and discussing about the rolling example where we had arrived at this formulation here, where we actually tried to look up into what is going to be the plane strain condition for this particular rolling, so that we could substitute for the value of sigma x as we had obtained earlier. This is sigma x, I'm sorry, for in the earlier governing equation case. So let us now apply the von Mises yield criteria here. So let us say if we apply the von Mises yield criteria to look at what is going to be the condition for which plastic flow can be initiated, we have here sigma x minus so basically the criteria says sigma 1 minus sigma 3 sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 whole square should be greater than or equal to, in this particular case it should be equal to 6k square. I think I had evaluated this condition earlier looking at the strain energy model or the deformation model, and here in this particular example, if we just substitute the values of the various sigmas, so sigma 1 is basically sigma x in this case, sigma 2 has just been found out to be half of sigma x minus pressure P, so square of this plus you can say again half of sigma x minus P plus P square plus minus P minus sigma x whole square should be equal to 6k square, or in other words we have actually if we just looked at, or if we just algebraically solve this, it'll basically lead us to 1/4 of sigma x plus P square plus 1/4 of sigma x plus P again whole square plus P plus sigma x square should be equal to 6k square, or in other words P plus sigma x can be recorded as twice k. Okay, so that's going to be the condition for von Mises yield criteria to hold, where there can be a relationship between the ultimate shear yield stress k and the the roll pressure as well as the principal stress sigma s x. So basically now if I put P plus sigma x equal to 2k from the last relationship, I have value for sigma x principal stress in terms of the maximum shear yield stress of the material twice k minus P. So you're now indicating a variable sigma x of the rolling process in terms of a material property k and also the roll pressure P, and that's going to be our goal here, to ultimately solve the governing equation. So the governing equation can now be changed to d by d theta of just substituting the value of sigma x here makes it twice k minus P times of y, okay, minus of, and please understand also one more issue is that the change in the direction of the friction force should happen before and after the neutral point. So in one case the whole frictional term, as has been suggested here in this equation, this is the frictional term related to this equation. So this is a sort of an enabler, and in the other case after the neutral point has been crossed over, this should be a disabler. So we should consider the plus sign here. You remember the way we had in some of our previous slide tried to enable or disable this frictional force. So till and until the value, this element reaches the neutral point where the velocity of the material is equal to the roll velocity, you assume the friction to be assisting in the rolling process, and beyond that obviously the roll velocity falls down, and the deformational velocity plus the infeed velocity, that is Vf, is more than the roll velocity. So there is going to be a disabler. So it's going to pull the material back because of the relative lower relative velocity or because of the positive relative velocity between the direction of the motion of the element and the wheel element. Okay. So because of all this, you have to go up to the neutral point for the friction to be enabler, and beyond the neutral point for a friction to be disabler for the rolling to happen. So in this event also here we have just changed this expression to plus minus to really get to so in one case I'm sorry, this has to be here. So in one case the rolling can be positive rolling before the neutral point, and in another case the extent of friction should be a disabler. So we have a plus minus mu term incorporated here, and so therefore we can say this as minus plus minus mu minus theta rp equal to 0. Okay. So if it is aiding the process before the neutral point, the sign of the friction coefficient is positive, and we are assuming that the friction coefficient is disabling the rolling process, or it's going to be in the direction which will prevent the rolling from happening. So that is why minus mu. Okay. Please understand this very carefully. So therefore we can write down this whole expression as if I make an assumption here that as the material is being rolled it undergoes strain hardening. So let us say as the material is rolled it gets strain hardened and also increased K values. On the other hand, you can say that because of the rolling process the Y decreases. On the other hand, because of the rolling process the Y decreases. So I can just assume the probably a condition where, well, although it is only an approximation, that if the strain hardening is not very huge, in that event it kind of remains valid numerically, that the Ky, that is with the increase in the strain hardening and the reduction in the sectional area, or you can say the sectional thickness of the material, may remain a constant, or maybe a constant and independent of the angle theta. Okay. So this is only a assumption. However, in actual rolling processes it may not be typically true, but in cold rolling processes where the friction doesn't get varied very much, and also we can assume the strain hardening may not be so drastic. Okay. This assumption still keeps valid. Okay. So if we have this simplification without resulting in much error, we can pull out the Ky term from here because it's now independent of theta, and we can write twice Ky d by d theta of 1 minus p by 2k. Okay. This whole expression here, plus obviously we would like to write this term in a little different way, taking out the minus sign here and writing theta minus plus mu, just opposing. So just changing signs on this plus minus. Okay. Times of rp, r times of the pressure p, r is the roll radius, p is the pressure p equal to 0. And having said that, I further try to find out for small theta how y can be expressed. So as theta is small, okay, we can easily say y to be represented as y equal to Tf by 2 plus r theta square by 2. So we can safely assume the r theta to be the element length, and obviously because theta is a small, this r theta is at an angle theta with respect to the horizontal direction, or at an angle 90 minus theta, the vertical direction. And if I look at such a illustration here, right here in this method where we are talking about this to be r theta, and this component of r theta to be r theta sine theta, okay, and sine theta can be approximated as theta. So therefore r theta times of sine theta is r theta times of theta, and that is going to be the addition which is going to be here, and therefore we can say that y can be estimated as Tf plus r theta square whole divided by 2. So having estimated the value of y here, if I substituted this y from the relationship, we would try to obtain again for the y, we can actually divide this whole expression by 2k. Therefore the expression comes out to be y times of d by d theta of 1 minus p by 2k, okay, plus theta minus plus mu times of r times of p by again 2k. I am dividing the whole expression by 2k equals to 0, or if I put the value of y further here as Tf plus r theta square, and obviously d by d theta of 1 is 0, so I can have this as minus of d p by 2k of d theta, and this divided by 2 plus theta minus plus mu r p by 2k equal to 0. Okay, so we can actually arrive at some logarithmic form as a solution for this equation based on all these criterias, and further I can multiply this whole expression by 2, so on both sides, so I have a twice coefficient introduced here equal to 0, or then I can actually rearrange this expression and write this d p by 2k divided by p by 2k, okay, p by 2k basically is equal to now twice r times of theta minus plus mu times of d theta divided by Tf plus r theta square. So if we were to integrate this final form for the solution, so we integrate this equation in the next step, we are left with integral of dp by 2k by p by 2k, okay, equals integral of twice r theta d theta by Tf plus r theta square, one component, minus plus integral of twice r mu d theta. We are just algebraically simplifying this expression, enabling it to contribute, and plus a c1, where c1 is the constant of integration. Okay, so we have c1 is the constant of integration. So having said that, now if we looked at the solution, this obviously would be okay. So this becomes equal to ln p by 2k, and this particular integral here, because obviously this is y, you have dy, so dy by Tf plus y becomes ln Tf plus r theta square, and then this particular integral would have solution. So basically you can this is actually a tan inverse integral, so this is going to be twice mu root over r by 1 times of 1 by root over Tf times of tan inverse r by Tf theta plus the ln of c by 2r, where c is a modified constant. Okay, so it would come up from just dividing this r mu. Okay, so you have Tf and then also dividing by Tf further, so that you can have a 1 plus x square, so dx by 1 plus x square formulation, of which tan inverse is the integral. So the argument there would come out to be root of r by Tf times of theta. Okay, and that's how you arrive at this formulation. So therefore, if this is going to be the final solution for the indefinite integral, the goal that we must have is to be able to estimate what is going to be the C value, for you to be enabling or for you to be able to tell about exactly what is the roll pressure which is needed to set forth the yield criteria of rolling, which is as per von Mises, as we have developed earlier, as P plus sigma x equal to twice of k, where k is the sort of you can say the ultimate shear yield stress of the material. So if we write this sort of in a clear manner, let's say we make a lambda which is equal to twice by root of r by Tf times of tan inverse of root of r by Tf theta. So we assume this as the lambda. So we are left with here a case where P by 2k can be estimated as some value C times of y by r. Okay, because you already know y to be equal to Tf plus r theta square. Okay, so y by r times of e to the power of minus plus mu lambda. Okay, so which is this particular term here. So basically we are talking about Cy by 2r, and also this would necessitate, so we already know that our initial pressure Pi of the roll plus the sigma xi, which is the initial reaction force in the inlet side of the roll, should be equal to twice k by the von Mises criterion. So therefore the Pi by twice k could be easily written as 1 minus sigma xi by twice k, and initial point, or at initial point, obviously the lambda I which is going to be there, okay, can be defined in terms of the theta I, which is going to be the initial contact length, okay, of the roll. So theta equal to theta I think I had illustrated this earlier, how theta I is that at snapshot at t equal to exactly 0, supposing the rolling process was already continuing and you have theta, at t equal to 0 you are taking a snapshot. So that's, it's basically the contact length that the roll would have at the beginning of the process with respect to the workpiece, which is actually the angle theta I. And so lambda I here can be recorded as twice by root of r by Tf tan inverse root of r by Tf times of the variable theta at the initial condition, which is theta I. So having said that, now if we assume the initial pressure, roll pressure to be Pi, and the initial principal stress to be sigma xi, K of course is a material property which is not getting changed much in this particular case. So we are left with P by 2k equal to C times of, so let's just substitute this corresponding to the initial condition. We have Pi by 2k. Let's assume the constant's value C to be C minus, okay. It's a constant of integration, mind you, which is also quite dependent in general with the theta here. So theta will change really this particular final formulation of C. So let's assume this value to be C minus. Constant of course will be something before the neutral point, and after the neutral point the constant would be C plus, okay. You already know that in one case the friction is an enabler, another case the friction is a disabler. So obviously this C value will be C minus before the neutral point has reached, and will be C plus after neutral point. So from calculation sake also, you're just changing the coefficients to plus minus 2 mu root of r. So assume C minus here, and y at the initial point is equal to the initial thickness Ti times r e to the power of, because the friction in this particular case is playing as a, because it's before the neutral point, it's playing as a enabler. We have minus mu lambda I, okay. And so from this expression we can easily get the value of I'm sorry, there is a 1 by 2 term here. You have to remember y is actually half the thickness, so actually y is Ti by 2, whether it's initial or final. That is how you represented y before. So we have the C minus value here calculated as, from this expression right here, as if I substituted again the value of Pi, which is 1 minus sigma xi by twice k. From this expression C minus comes out to be equal to twice r by Ti times of 1 minus sigma xi by twice k times of e to the power of plus mu lambda I. So that's how you calculate one of the constants before the neutral point has been arrived at. Obviously because of the change of value here, this constant would also significantly change value wise, and therefore, as I told you, before the neutral point and after the neutral point, because friction components are completely separate, the constant of integrations would be C minus and C plus in both the cases. So let us now apply this equation at the end of the rolling process to find out what is going to be the the region beyond the neutral point. So let's look at, so you know that beyond the neutral point the constant C is going to be C plus, and if I were to write the expression for the pressure, so P by 2K becomes equal to C plus Y by R e to the power of plus mu lambda, okay. That's how, because this is now an enabler, so the friction is a disabler, so therefore the value has to be plus mu lambda, and obviously the constant of integration is C plus, as I had earlier mentioned. So in this particular case, again at the final separation or at the end of the rolling process, if thickness is Tf, which has been achieved, the roll pressure Pf by 2K should be equal to 1 minus again sigma xf by 2K, where this is the final principal stress which is there on the sheet, and at the exit point, therefore I can easily have the theta I being equal to, again if I look at how we have formulated lambda here, so lambda is basically equal to twice root of r by Tf tan inverse of root of r by Tf times of theta, and I am saying that at the exit point of the roll the condition is corresponding to theta equal to 0, okay, because if I were to look at here, again let's go back to the earliest module where we were talking about such a theta. So the expression of theta equal to theta I is really for the initial condition up to the roll pressure, but at the final extent you can see the value of the theta is really from starting between O1 O and O and O, so the value here is 0 actually, okay. So in this particular, there is no angle when the formulation it leaves. So corresponding to this theta equal to 0, which is the exit condition for the roll where T equal to Tf, we can say that theta is 0, tan inverse 0 is 0, so the lambda becomes equal to 0 here, and we are left with this as 1, and 1 minus sigma xf by 2k becomes equal to C plus y is Tf in this particular case times of r, or because it's Tf, as I told you, y is actually Tf by 2, initial thickness by 2, that's how y has been designed. It is from the origin, which is located centrally across the neutral axis all the way to the end of the element, so Tf by 2r. And in other words, we have the C plus here estimated after the element passes the neutral point, estimated as twice r by Tf times of 1 minus sigma xf by twice k. So these two are very important for us because we would like to apply these to what is going to be the pressure before the neutral point and what is going to be the pressure after the neutral point. So a set of values which emerge because of all this calculations is that at so I just write it down as before neutral point and after neutral point. I have the p by 2k value, we just write this before here, as, if you may remember, it was c minus y by r e to the power of minus plus mu lambda, and that corresponds to, if I just substituted the value of c minus here from the expression done earlier, where c minus is equal to twice r by ti 1 minus sigma xi by 2k times of e to the power of plus mu lambda I. Okay, so this is actually minus, I'm sorry, this is minus. Okay, because as I told you before the neutral point the friction is enabler, so minus mu. So if I substituted this value for c minus in this particular expression, the final form which emerges here can be represented as twice y by ti, where ti is the initial thickness of the roll. Sorry, let me just take it off to a different place. Okay, here twice y by ti times of 1 minus sigma xi by 2k e to the power of mu times of lambda I minus lambda. And after this rolling beyond the neutral point or after the neutral point, the p by 2k becomes equal to twice y by tf times of 1 minus sigma xf by 2k e to the power of mu lambda. So that is how you can estimate the roll pressure before and roll pressure after. And in fact, if we really wanted to determine what is going to be the pressure at the neutral point, so you can really either use the equation before or the equation after to actually look at what is going to be the pressure after and before the neutral point. Obviously, physically what it would mean is that there is a continuity, there is a pressure continuity in the way that the element is going towards the neutral point and beyond the neutral point. And so at that particular point where theta equal to theta n, or theta is the neutral point, the pressure before and after should exactly be the same. So there is one continuity of the pressure, otherwise there is a pressure step, and that's not what really happens or what is there in the actual situation. So therefore I can say that I can probably at neutral point do some analysis here to calculate what is going to be the value of that lambda corresponding to the neutral point. So from looking at both the equations, so I actually can predict the lambda equal to lambda n by equating the equation before and after, that is p by 2k before, which is actually equal to twice y by ti times of 1 minus sigma xi by twice k e to the power of mu lambda I minus lambda neutral. Let's say we are at lambda n, and that is equal to p by 2k after, which is actually twice y by tf times of 1 minus sigma xf divided by twice k to the power of mu lambda neutral. So if I equate these two expressions together, we can find out by taking natural logs on both sides lambda n value, which comes out to be half 1 by mu natural log of tf by ti times of 1 minus sigma xi by 2k divided by 1 minus sigma xf by 2k, can just close this, okay, plus the lambda I value which was incorporated earlier from the p by 2k before equation. So that's how you find out the lambda neutral. Obviously the lambda neutral corresponds to a position which is corresponding to 2 by r or 2 times of root of r by tf tan inverse of again root of r by tf times of theta neutral. And so I would be able to enable, or I would be able to sort of calculate using the lambda n value what is going to be the neutral angle, okay, of a particular element in a rolling condition. So with this I would like to sort of end this particular module. I am also going to look at probably how to determine the roll separating force, or how what kind of torques can be used, or what kind of power loss in the bearing would happen. But here you could actually have a very good estimate of the rolling pressure which is needed to calculate all these different values related to power dissipation while rolling. So with this I would like to sort of close this module. In the next module we will like to look at again the roll separating force or the power transmitted in the bearing, and then maybe if time permits we will do a little bit of some forming processes and just schematically mentioning what the process is like. In fact this kind of a modeling has to be translated everywhere, whether it's forging or extrusion or deep drawing etc., as I have shown for the rolling. And then we will also like to have a small introduction to additive manufacturing, and beyond which I will show you a video in the lecture 48 or module 48 where we can actually use the FDM Titan to rapid prototype a part or 3D print a part which is very small. So with this I would like to conclude. Thank you so much again for being with me. See you in the next module. Bye bye.